Interpreting simulation results, histogram. After a simulation has been run, we can start doing some basic interpretation on the charts and reports being generated here. 72. With your cursor on top of cell K21, click on the Browse Results icon on At Risks ribbon. This should pop up the only output it has defined, total cost. With several other outputs on the model, the tabulation key would shift to the next output chart. This window shows the histogram generated after 10,000 iterations for total cost. Observe on the right-hand side of the chart the statistics grid showing various statistics calculated on total cost. Some significant information can be read out of this chart. On average, the mean, the total cost for this project would be close to $118,000. Results range from a minimum of approximately $91,000 to $164,000. Observe that at risk by default places two vertical delimiter lines at the 5th and 95th percentile. The respective levels for these two percentiles are roughly $104,000 and $135,000. This means that there's a 90% confidence the total project cost will range between those two levels. The most likely amount or mode is slightly smaller than the mean value of $113,800. This difference tells us of asymmetry. Whenever the three central statistics, the mean, the mode, and the median differ between each other, then there is asymmetry present on the distribution. The drag towards the right-hand side of the distribution, or positive skewness or asymmetry, makes that the mean or average result of all 10 possible iterations is somehow shifted towards the right tail of the distribution. In other words, unlikely events of extremely high costs drag the mean apart from the most likely outcome of $113,800. On the other hand, the median or 50th percentile at roughly $117,000 means that half of the possible results may be smaller than such a value, whereas half of all possible results may be larger than it. As a matter of fact, a skewness statistic of positive 0.5286 indicates a relatively larger weight of the distribution towards the right-hand side of it with respect to the left tail. We can now drag the two vertical delimiters or lines at different points of the x-axis. Notice how, by dragging to different points these two vertical delimiters, the cumulative probabilities being shown on top of the probability bar dynamically change. At any point, the sum of all three segments of the probability bar will always add up to 100% total probability when splitting any three segments being defined by these two delimiter lines. 73. On top of the left delimiter, change whatever value is on for $109,700. Remember, this figure represents the deterministic amount, including most likely figures, for each one of the 10 activities plus the E and V of the three additional eventual risks. 74. On top of the right delimiter, change whatever value is on for $115,000. Recall that this amount stands for the total project cost with the addition of an arbitrarily chosen contingency reserve as a percentage added to the total activity costs. The chart should now look like this. There exists an approximate 20% probability the total project cost will be smaller than the cost being calculated with E and V's for eventual risks. In other words, if contingency reserve were to be established at $109,700, there is an 80% probability that such an amount would not be enough. That is, in 4 out of 5 possible cases, this contingency reserve is not enough to cover project cost variability. If contingency reserve were to be established at $115,000, there would be an approximate 40% probability that it would be enough. In other words, under this arbitrarily established figure of $115,000, there's a 60% probability that it will not be enough to cover eventual costs. Notice that we have first established a given level for our x-axis variable, the total cost, and then at risk has calculated the respective cumulative probability assigned to such a level. Notice that probabilities interpreted on these density curves or histograms are measured as areas under the curve for any given segment. From a probabilistic point of view, we usually turn the question around. Instead of calculating a probability or confidence level for a given x value, we present a given confidence or probability level and let the software calculate its respective x value. For example, if we want to be 80% confident that our contingency reserve will be enough to cover our project inherent variabilities, then we change the value on the probability bar. 75. Click on top of a probability number sitting on the right-hand side of the probability bar. Replace that percentage number for 20%. We are, therefore, leaving 20% of the probability of a certain x value to the right-hand side of it. Thus, we are dropping 80% probability level at its respective left-hand side. The value on the x-axis calculated on top of the vertical delimiter should now be of $125,828. In other words, if we plan to be 80% confident that a certain total project cost amount will be enough to cover for the inherent variability of the activities and the eventual risks, then we should plan to allocate a total amount of approximately $126,000. Surely 26% above the $100,000 mark first established upon the variation of quantities and unit prices for the 10 activities that composed the project. Notice how the total project cost changes by modifying the required confidence level. At 90% confidence, the level is approximately $131,000. At 95% confidence level, the figure rises to $135,000. At 99% confidence level, the total project cost would be budgeted at $144,000. Many other competing bids would favor another more aggressive contractor willing to bid cheaper with less certainty involved.